We're going to describe here the Koopmans theorem, which, by the way, he got this theorem while doing the PhD in physics, and then he switched to economics, and actually he got a Nobel Prize in economics in 1975. So we already derived the Hartree-Fock equations. These are the Hartree-Fock equations, and here we want to analyze if these Lagrange multipliers appear in these Hartree-Fock equations, if they do actually have any physical meaning. This is the question that we want to answer, and the answer is going to come through the Koopmans theorem. It's important to insist that here these Hartree-Fock equations, they are not equations corresponding to solving the eigenfunctions and eigenvalues of any Hamiltonian. These are not a Hamiltonian. They look like a Hamiltonian, but this is not the equations we are getting for solving the wave functions and the eigenstates and the eigenvalues of the Hamiltonian. So which are these Lagrange multipliers actually? And the answer, as I said before, it's coming from the Koopmans theorem, which basically states the following. This EK, the Lagrange multiplier, corresponds to state CK, is within the Hartree-Fock approximation. That's the context we are going to use in order to derive that expression. It's basically the energy for the n-electron system minus the energy for n-1 electron system, considering that the electron you are removing from the system is in state CK. And we are going to prove that. Or we can put in another way. We know that ionization energy corresponding to extract one electron in state CK is given by the following expression. Basically, is the energy of the final state energy, which corresponds to the energy with n-1 electrons, and considering that the electron you're removing is in state CK, minus the energy of n electrons. And that's given by, considering that result here, that's given by minus EK. So minus EK, it's basically the ionization energy corresponding to extracting one electron in a state CK. So in the following, we are going to prove this Koopmans theorem. So basically, for that, what we have to do is, okay, we are going to analyze these two terms here. We already have had an expression for the energy of this n-electron system, which basically is the average of the Hamiltonian when you're using the minimizing wave function, the Slater determinant for the Hartree-Fock equation. We already have an expression for that. And now we go and we want another expression for this system, for n-1 electron system. In principle, what you should do is you should solve again the Hartree-Fock equations from the starting point, considering the Slater determinant with for n-1 electrons, minimize the system again, and get new wave functions. Of course, that's quite complicated, or it takes a lot of time. And we are going to make here an approximation. An approximation we are going to make is that when you are removing one electron here, there is no, from the system, when you want to have this n-1 electron system, there is no electronic rearrangement. Therefore, the other states are going to be the same as the one you got for solving the Hartree-Fock equations for any electron system. So what we are going to do, therefore, basically, in order to solve and to analyze this n-1 electron system, we are going to build a new Slater determinant, but in this case corresponds to we are going to use n-1 states. So, and the states we are going to use in order to build this Slater determinant are going to be the states that were minimizing the system with n electrons, and we are removing from here everything which is related to state CK. For example, you can see here in this row here, you don't have the variables corresponding to state to electron Rk. It goes from Rk-1 to Rk+1. Then on the other hand, in the other row, there is no row corresponding to state ck. So basically we are removing a row corresponding to a state ck and a column corresponding to the variables rk. And therefore, you have a determinant of n minus 1 times n minus 1. Therefore, you have a new renormalization constant for that. Okay, so once you have this Slater determinant, what you have to do is considering the same Hamiltonian as you had before, but using this wave function, you have to solve or calculate the average of the Hamiltonian using this new wave function corresponding to n minus 1 electrons. And this is actually very simple to do. Actually, you can use the same formula you have for n electrons, and basically you have that in the summations appearing in this formula. The thing is that as there is no state k, you don't have a summation, you don't have a contribution in the sum associated to state k. So the expression you have for that is actually quite straightforward once you have the expression for n electrons. Now we're going to derive an expression for the difference between the energy corresponding to n electrons and the energy corresponding to a system with n minus 1 electrons. Everything within the Hartree-Fock context. So we're going to divide that in order to make it much simpler in 3 different contributions. The first one, first contributions to the energy, of course. The first one, we have the sum of the kinetic energy and the interaction with the ions. You make the difference between the system of n electrons and the system with n minus 1 electrons, and the only term you have is the contribution associated to state ck, because actually you have the summation. It's also included in the state with n electrons, but it's not included here in the state in the system with n minus 1 electrons. So therefore, when you're making the difference, the only remaining one is the state k. Okay, when you are doing the difference associated to the Hartree contributions, the difference between a system with n electrons and n minus 1, here in these Hartree contributions you have a summation over 2 over I and j states, as one of the states is going to be k, and you just have a summation over the other states, and one of the summations is removed, because actually, as I said before, this summations over state k is included here, but it's not included here. Again, the next term we are considering here is the exchange contribution, and this exchange contribution also has a double summation. And again, as it happens with the Hartree contribution, then one of the summations is going to be removed because the state is going to be the k state, and you just have one of the summations. So therefore, the sum of these 3 contributions is going to give you the energy difference that we were looking for, the energy difference between the state with n electrons and the state with n minus 1 electrons. The one you're removing corresponding to state ck. So what has to do this expression? You have the sum of these 3 terms with ek. How can you relate the sum of these 3 terms with ek, the Lagrange multiplier associated to state ck? So in order to see that relation, we have to go back to these Hartree-Fock equations corresponding to state ck, which is this expression here. And we are going to do here is we're going to isolate somehow this ek. And how we are going to do that? We are going to make the scalar product of the whole equation with that state, with the ck state, which I could remember that involves either the special integral and the summation over sigma states. When you do that, it's actually very simple. You can see that here on the right hand side, remember that these ck states are normalized, so therefore making the scalar product with the ck state, you have that's going to be 1. So basically the only term remaining on the right hand part is ek. And when you're doing the scalar product on the left hand side, you actually have the same expression of the corresponding to the sum of these three terms here. So therefore, this way we are proving that Ek it's actually the energy difference between the state with n electrons and the system with n-1 electrons, considering that the electron you're removing is in state Ck. Of course, it's important to insist that that kind of calculation or that proof is based on the Hartree-Fock context. And besides that, we are considering that there is no electronic rearrangement when you're removing an electron for the state. And this approximation, of course, the validity of this approximation, of course, it's going to depend on the system, but the kind of result you are getting are actually not very far from the experimental results, because actually that results, which is going to be related with the ionization energies, it can be measured.